receiving end voltage and receiving end currents. So we have to calculate sending end voltage and sending end current. So for that we have to apply Kirchhoff's laws, KVL and KCL. Because of each load variations, to write KVL, KCL are very difficult. That's why transmission line we are going to define it with ABCD parameters. The reason we will see in depth. So first let me explain about how to define ABCD parameters for a transmission line. A transmission line is having parameters. So one transmission line. To this transmission line, receiving voltage, receiving current, sending voltage, sending current. If I written this in matrix forms, then ASB is equal to ABCD parameters. We are receiving matrix. The size of this matrix is not 2 by 1, size is 2 by 2, and the size is 2 by 1. So from the 2 by 1. So everyone enter parameter. If written equations, then this V is equal to AVR plus VVR. This is equal to CVR plus DIR. Like this equation, forget. Now, to get parameters, first total analysis. Here we are going to do receiving end side. Total analysis we are going to do receiving end side. In first case, here I am going to assume, I am going to representing, I am going to open circuiting receiving end and transmission. Receiving end side I am going to open circuit, receiving end side. Open circuiting. You know what happens in open circuit condition? In open circuit condition, what happens? Voltage will adjust, current becomes 0. Means receiving end I am going to making open circuiting means receiving end voltage IR is equal to 0. No current will flow in open circuit condition. If I open circuited receiving end side, what I can get here? The equation. This is equation 1 and equation 2. This equation we will get by applying Kirchhoff's voltage law. This equation you can get by applying Kirchhoff's current law to the transmission line. Now, if I open circuit, what I say receiving end side current is 0. The equation you can get as Vs is equal to A into VR. Because IR 0 means V voltage. So this VR is called open circuit voltage. This VR, I am going to define the open circuit voltage with VR naught. This VR naught is called open circuit voltage. Open circuit voltage. So from this I can define VR naught is equal to Vs by A. Vs by A. And here para A parameters I can define as A is equal to Vs by VR naught. So ratio of voltages, and voltage what sending end and receiving end. Input voltage and output. This I can call it as inverse voltage gain. Inverse voltage gain. Units? No units. Because voltage, no units. Inverse voltage gain. And here this VR naught. I can define Vs is also as Vs is also equal to VR naught into just keep in mind VR naught into A. Now the second case. The second equation. If I open circuited, IR the current becomes 0. There I can get as calculator. See here. Is I can define as Is is equal to C into VR. Circuit is opened. Circuit, how can define Is? Because Is is equal to source current is moving because of through capacitors. So this current is also equal to charging current. AC charging current. Important charging current we can call this IC. So this charging current or sending end current is equal to C into VR, and how you define Vs divided by. So sending end current or charging current or open circuit condition also we define with this expression. Now here in this condition, parameter C we can define with formula as C is equal to Is by VR naught. Is by VR naught means ratio of current to the voltage. Ratio of current to the voltage is nothing but what? Inverse of impedance. So this we can call it as transfer admittance. Transfer admittance. Because inverse of impedance is admittance. Transfer admittance. In which condition? In open circuit. In open circuit condition. Transfer admittance. Units are moles or series. Units are moles or series. Now in second case, I am going to analyzing the receiving end side with a short circuit. Right? Short circuiting, receiving end side, receiving end side. In short circuit condition, which quantity becomes 0? Voltage, receiving end voltage becomes 0. Receiving end current becomes short circuit condition. The characteristics of short circuit condition are resistance 0, voltage 0, current will exist. In open circuit condition, the characteristics of open circuit conditions are voltage exists, current is 0, resistance is infinity. Now here I am going to short circuit in secondary side. Means we are making 0. So the equation 1 becomes. So Vs is equal to under VR is equal to 0, which is equal to BIR. B into IR. So this B term we can consider as B is equal to this IR is also called short circuit current ISC. So B is equal to Vs divided by IRAC, receiving in short circuit current. So this we can call ratio of voltage to current is also called impedance. So this is called transfer impedance because input voltage, output current we are considering. So we can use term transfer impedance. It is called transfer impedance. Units are under short circuit condition. Units are ohms. Now the equation 2 becomes. Is equal to D into IR or IRAC, short circuit current. So D is equal to what here? I can define D is equal to IS by IRAC. So input current by output current. Here also I can use the term transfer. Inverse and the ratio of current to current. So current gain how we define? So output current by input current, but here reverse. I can call it as inverse current gain. The units are no units. Current by current, no units. So the ABCD parameters we can come like this to the any transmission network. Now come to in-depth analysis of each and every transmission line separately. So first come to short transmission. So before going to define short transmission lines, I am going to give you some important notes. These notes we can use as a formulas. Note 1. I am going to consider one series impedance network. This I can use as formulas while designing transmission lines. Series impedance network will be like this. So as a series impedance network. Transmission. By seeing you can say there is no capacitance means it's a short transmission line. So series impedance. So as this has a V1, this has otherwise sending in current, sending in voltage. receiving end voltage, receiving end current, receiving end current. Now I have to define ABCD parameters for this series impedance network. So for that we use node KVL KCL. Without knowing ABCD parameters, we use KVL and KCL. If I written KVL equation there, how many loops are there? Only one. If I written KVL equation, what you can get? Supply voltage Vs is equal to Is into Z plus VR. And the KCL, if you written, what you can get here? Supply voltage is equal to receiving end current. Why? Because the network is connected in series. So it is called series impedance network. Now if I written this equation, if I rearrange this equation as Vs is equal to VR plus this Is is also equal to IR into Z. And this equation becomes Is is equal to VR is 0 there. So I can write this as 0 into VR plus IR into 1. Alright. Now I can write this in, if I written this in matrix form, Ds Is is equal to what I am getting 1 Z 0 1. Remember students, very important analysis this is, and VR IR is written in matrix form. Taking these equations by using KVL, I wrote here this equation, KVL equation. This voltage equal to sum of this voltage and this voltage. This is what impedance. So impedance into current is nothing but voltage. So how much voltage gives Is into Z or IR into Z? Because Is is equal to IR here, connected in series. Right? Now these parameters are called ABCD parameters of series impedance network. Keep in mind, very important. This you are going to calculate with short transmission line. Yes, sir. Short transmission line. Yes, why? Because there is no capacitance. For the short transmission lines, the sending end current is nothing but what? Sending end capacitor current if you want. Charging current. Charging current, how you defined formula? Charging current is equal to charging current. Sending end current, how you define for short transmission line there? Sending end current is equal to Is is equal to C into VR naught. C into VR naught. See, if you written here, sending end current and charging current is equal to current flowing through the capacitor. If there is no capacitor, means what? Current flowing through the capacitor is 0. C0 had difference. C into VR naught. What is the C magnitude here? C is equal to 0. So 0 into anything. So charging current is 0. There is no capacitance effect. Short transmission. Now, note 2, the same analysis. Note 1, what you have to observe is to the series impedance network, the transmission network will be ABCD parameters will be like this. Similarly, if you take a note 2, parallel impedance network, shunt admittance network. If I consider admittance Y here. If I consider supply voltage Vs, sending end current Is, receiving end current IR. If I consider load, receiving end voltage is VR. Receiving end voltage is VR. Now to this network. So if Is current flowing here, how much current will flow here? These two are connected in parallel or these two are connected in parallel. The existed current is how much here? Vs or VR into admittance. Yes, or we are into admittance. If it is impedance, I is equal to V by Z. So 1 by Z is nothing but admittance. That's what I define it. The current flowing through the shunt path. Now, to this, if I written KVL equation, I have to define ABCD parameters for the shunt model. If I written KVL equation, what I can get here? Vs, this Vs is equal to, Vs is equal to, I am writing this equation. If I write what I can get here? Is equal to, now element only one element. How much voltage is existing here? VR into Y. Now, if I written KCL equation, here, so Is is equal to, how you can define that? Is is equal to sum of these two currents, IR plus current flowing through shunt. That current is nothing but what? VR into Y. If I rearrange this equation in terms of VR and IR, here IR term is how much? 0 into IR. Here IR term is what? So if written VR in terms of VR, we have VR into Y plus IR. VR into Y plus this voltage is sorry, what is the voltage existing? The voltage equation of it means VR only. Vs is equal to VR of this voltage. R. So this is not current magnitude. This is not the voltage, current magnitude. Right? Now we can get matrix for this network as is equal to VR term is 1, current 0, VR term here is Y, current term is G, current term is 1. These are the IVR. These are the ABCD parameters of shunt branch. These are called ABCD parameters of shunt branch. You have to keep in mind always while designing transmission lines. Now case 3. Now here I am going to connect cascading. Cascade connection or tandem connection is nothing but I am going to connecting one series impedance network and shunt admittance network. Cascading means neck to neck. One network after that another network we have to connect. The connection is called cascade connection or tandem connection. Remember, tandem connection. Tandem or cascade connection. Now, to this cascade connections, we have to define ABCD parameters. This is what series impedance. This is what shunt. This is shunt admittance series. Shunt admittance network. Now, say this is supply voltage, sending in voltage, sending in current, receiving in voltage, receiving in the current. Now, what are the ABCD parameters for this series impedance network? I want Vs, Is is equal to Vs, Is is equal to. What are the ABCD parameters for this? 1, Z, 0, 1. And what are the ABCD parameters for this network? 1, 0, 1 by Z or Y, 1 into VR IR Now, if you multiply these two, you can get ABCD parameters for one series impedance and one shunt admittance connected in cascade. We can get ABCD parameters. How we can get ABCD parameters by multiplying these two? What you can get here? The ABCD matrix as ABCD matrix. If you multiply, what you can get? 1 into 1, 1 plus zy, 1 plus yz or zy. This is 0 plus z, the 0 plus z, and this is 0 plus y, and now 0 plus y. These are ABCD parameters for if you cascaded these two transmission lines. Verify, I made any mistake there? No mistakes. Now, see series impedance network, ABCD parameters are this. What we discuss the symmetric condition for Z matrix. If Z11 is equal to Z22, it's also called input driving point impedance is equal to input driving point impedance of the network is equal to of the two-port network is equal to output driving point impedance. Then we can call that network as symmetric network. Means ZSS is equal to ZRR receiving end side. ZRR. Now ZSS means input side. But V1, if you did this as V1, I1, ZSS is nothing but or Vs by Is. ZSS for series impedance network is not 1. So this 1 is equal to, this 1 is nothing but A. A is equal to, and ZRR is nothing but 1. ZRR is 1, means A is equal to D. Then we can call that network is a symmetric network. That network is a symmetric network. You make it out. Why A is equal to D only we can call it as a symmetric network for a transmission line. So the main important reason is there. If we return Z parameters, in terms of very important point, when students are getting confusions there. If you turn these impedance parameters in terms of T parameters, what you can get? A by C, delta T by C, 1 by C, and D by C you will get. Z parameters in terms of T parameters we can define like this. See here, these two terms are equal or not? Because A by C is equal to D by C. Then we can say this Z11 is equal to Z22. This is Z11 T parameters in terms of impedance, Z22. So A by C will become cancelled. A is equal to D. So with this analysis, if A is equal to D, then we can call that network is a symmetric network. So series impedance network is nothing but what? It is a symmetric network. Now come to shunt branch element. See here also A is equal to D, means we can say this is also symmetric network. Now come to verification of reciprocity condition. So I will analyze here for the reciprocity. Now come to this tandem connection and cascade connection. If you connect two connected cascade, these two are symmetric. No, because here A is equal to this, B is equal to this. Means if two symmetric networks are connected in cascade, it may or may not be a symmetric network. You can't call it as a symmetric network. Mostly may or may not. By complete analysis only we can say the network is symmetric or not. Now come to reciprocity condition. So reciprocity definition is there. Reciprocity condition. We can call any network is a reciprocal network if the network is having single independent source and there should not be a dependent source. Then we can call it as a reciprocal network. That's the basic definition for reciprocity theorem. Now, if you consider impedance network, if Z12 is equal to Z21, then we can call it as a reciprocal network. If any network is satisfying this, the transfer impedance of sending end side is equal to transfer impedance of output side. That's the basic definition for reciprocity. Transfer impedance of input impedance. Transfer input impedance is equal to transfer output impedance. Now here, what is Z12? What is Z12 here? In content Z is equal to 0. Z is equal to 0. AD minus BC. Okay. Z12 is equal to Z21. If it is a impedance network. Now we are going to find T parameters. T parameters in Z parameters in terms of T is nothing but what? These two. So delta T by C is nothing but equivalent to Z12 in terms of T parameters, which is equal to 1 by C. Z12 is equal to Z12. C will get cancelled. C will get cancelled. So finally, if delta T is equal to 0, if delta T is equal to 1, then that T network we can call it as a reciprocal network. So delta T is nothing but what? AD minus BC. AD minus BC is equal to G1. If AD minus BC is equal to 1, then we can call any T network, transmission network is a reciprocal network. Now come to this series impedance. What we are getting? AD is nothing but 1. AD minus BC is nothing but 0, which is equal to what? 1 we are getting. Means we can call series impedance network is a symmetric and also reciprocal. Come to shunt branch network. Here also if you see AD is nothing but what? 1. 1 minus 0 is equal to 1 means we can call this also a reciprocal network. This is symmetric and also reciprocal. Now come to this. If you cascaded two transmission, one is series impedance, one is shunt impedance. If you observe from the terminals, here you are going to see impedance and impedance. If you observe from this terminals, you are going to see only admittance. We can say simply by saying this simple network also, we can say it is not a reciprocal. If you compare our condition, if I compare condition, what is the ABCD parameters of this tandem network? These are the ABCD parameters. Here A is equal to D, are you observing? Not observing. Means you can say it is not a symmetric network. You verify reciprocal condition. Here what is AD? AD is equal to what? 1 plus YZ into 1 is 1. AD minus BC is equal to what? YZ, which is equal to 1. Which is equal to 1. Means here the network is reciprocal network. If it is not symmetric, it may accept reciprocal conditions. Just you have to keep in mind how to identify reciprocal symmetric conditions and then how to define ABCD parameters. We have to keep in mind to define ABCD parameters for all transmission lines. This is about analysis of transmission networks. Come to analysis of short transmission lines. Come to complete analysis of short transmission lines. Short transmission lines. The total network of short transmission lines is short transmission lines. There is no capacitance, only resistance and inductance. Sending in current, sending in voltage, or receiving in voltage, receiving in current, receiving in current. So, RL number 1 of short transmission line. Now, to this transmission line, we have to define ABCD parameters. ABCD parameters. So, the sum of these two nothing but what? Impedance. Impedance. Now, if I written KVL equation here, what I can get here? VIS into Z plus VR, which is equal to what? Supply voltage. Similarly, supply current IS is equal to what here? IR. IS is equal to IR from Kirchhoff's current law. Kirchhoff's current law. Very simple analysis. Here I am going to apply to calculate ABCD parameters KVL, KCL. Now, if I write this in matrix now, you can get matrix like this. VSIS is equal to C here. VR term is what? A is equal to 1 and IS term is what? This IS is also equal to why? Because IS is equal to IR is Z 0 1 into VR IR. Or simply short transmission line you can calculate series impedance. For series impedance, what are the ABCD parameters? These are the ABCD parameters. ABCD parameters for short transmission lines. Now we have to calculate voltage regulation. This voltage regulation is also called what? Per unit voltage regulation. So per unit voltage regulation is equal to receiving end no load voltage VR0 minus VR magnitudes divided by VR. This VR0 how you define? No load receiving end voltage also equal to ratio of Vs by parameter A minus VR by magnitude of AR. According to definition, if you want in terms of percentage into 100. While in this formula, we will calculate voltage regulation for short transmission. Now the important analysis is we have to draw phasor diagram. Phasor diagram. Before going to drawing phasor diagrams to this short transmission line, we have to know first for what quantities we have to draw vector diagram and in which direction we have to specify vectors. Vector diagram we draw. Generally vectors rotate in which direction? Anti-clockwise directions. If you taken any as a reference, so say one reference you are taking 0 degrees. Next if you are moving with this x-axis, y-axis, how you define this angle? Plus 90 degrees. Why? Because from this you are going to move in which direction? Anti-clockwise direction. And this angle is 180 degrees. And this angle is how much over representing? 270 degrees. In which direction? Anti-clockwise direction. Means we can say vectors rotates in anti-clockwise direction. If you want to move in clockwise direction, but this angle, this 290 is also equal to minus 90. So this is also equal to what? Minus 270. minus 270. Means with this analysis what we are going to is vectors moves in anti-clockwise directions. Vectors moves in anti-clockwise direction. Now while drawing vector diagram for any not only transmission like a transformer or generator, motors, any, while drawing phasor diagram, in the phasor diagram we are going to representing currents, voltages and the fluxes only. Voltage and fluxes only. Why? Because these are having same frequencies. What we discussed, vectors rotates in anti-clockwise direction with the constant speed. If those are moving constant speed, then only we can define vector diagram. Why? Because if any current vector is moving with 1000 rpm, and any one voltage vector is moving with 2000 rpm, at this condition, this is the difference. After some time, it changes. That's why those has to move with the constant. Vector has to move with the constant speed. The speed related term in electrical engineering is frequency, because frequency depends on speed. So speed related term in electrical engineering frequency. That's why the quantities which are having same frequencies, for those only we represent vectorially. Now with this analysis, first how to design phasor diagram or vector diagram, because to the vectors only, for all vectors we are going to define vector. That need to have magnitude and need to have direction. If any voltage source we are going to define, means voltage magnitude we are representing how much voltage, 200 volts, 300 volts. Similarly, polarities we are defining or not, which is positive or which is negative, that represent direction. Similarly for currents and also for fluxes, magnitude and direction we are going to define. That's why voltage, currents and fluxes are called vectors. Even power is also vector quantity, but we are going to not defining power here. Why? Because power is having double the frequency of voltage, currents and frequencies. That's why we are not going to defining power as in vector diagram, but even the power is a vector. Why? Because it is having magnitude, some 50 megawatts, 30 megawatts we are going to saying, and also we are going to defining in which direction power is transferring. So power is also a vector quantity, but we want to specify power in vector. Why? Because it is having more double the frequency of voltage and currents. Now first we have to identify how quantities are which is lagging and which is leading. So I am going to take voltage as a reference, voltage vector as a reference, and I am going to define a current at exactly with this current. Now if I take voltage as a reference to reach current, and which direction you are going to move in, and clockwise direction. Clockwise direction we are going to represent with negative angle or positive angle, negative angle. So minus 90 degrees. Means we can say with respect to voltage, current with respect to the current lags voltage by an angle 90 degrees. Otherwise, if you define current as a reference, if you want to represent voltage, which direction you are moving clockwise direction, anti-clockwise. Anti-clockwise you are going to define with positive 90 degrees. Means we can define with respect to the current, voltage is leading. Otherwise, to understand it, two vectors like this. This is 1, this is 2. Now, with respect to this, 2 is what? Leading and lagging. How we are moving clockwise? Clockwise means lagging. With respect to 2, 1 is leading. Like that we identify lagging and leading quantities. Now, if I draw a vector diagram for shunt transmission, I am going to draw, which is known term here, receiving end side terms are known. That's why first I am going to taking VRF reference. If you want, you can take ARF reference. VR I am going to take as reference. Receiving voltage we will take as a reference. Now load. All our loads are, we discussed already, loads are of two types, static load and dynamic loads. Static loads are the examples for resistors, resistive loads, stationary loads like heaters, lights and all. Dynamic loads examples are all rotating loads. All rotating load means fans, induction motors. All. In those loads, static loads are taking maximum 10% of our generating power. Nearly 90% are taking by inductive loads. That's why by default we can say all loads are inductive loads. Even though it is a RL network. If it is only inductive, current vector we have to represent 90 degrees. If it is a pure resistive, we have to represent in phase. But it is what RL network. That it is having more inductive nature. So that's with this knowledge I am going to defining IR vector like this. Current is lagging or not? If you take a reference as voltage, you are going to moving clockwise means lagging. The phase difference between these two is called receiving and phase angle. The phase difference between these two, is called receiving and phase angle pi r. Cos pi r is called receiving in power factor. receiving in power factor. Receiving in power factor. If power factor is not lagging or leading, lagging power factor. Because all our loads are lagging. Practically, we are not having anywhere capacitive loads. With this analysis only, every transmission it will represent receiving end voltage, receiving end current lags in receiving end voltage. Now, so this is IR. See, for short transmission on IR is also equal to what? IS. IR is also equal to IS. IR is also equal to IS. Now here, so if current is going, resistive drop will exist. So this resistive drop is not because of receiving end current. So this is always in phase with this. This is always in phase with this. This is what? IR and R drop. IR and R drop. Now here next inductor. So you know the phase difference between resistor and inductor. Resistor are going to be real axis. Inductor is nothing but J omega, frequency term J omega. We discussed already. You know XL, how you are going to find XL is equal to 2 pi FL omega L. This frequency existing numerator means plus J. Plus J means plus 90 degrees. So with this exactly 90 degrees. Now the transmission is having inductance magnitude more compared to resistance. So we differentiate this with maximum magnitude. Maximum magnitude. This is what IR into etc. IR into etc. The vector sum of these two nothing but IR or IS into Z. IR or IS into Z. IR or IS into Z. Now if you see this given equation, Vs is equal to what? IR into Z plus VR. VR plus IR into Z. The resultant is called what? Supply voltage vector Vs. The angle between these two is called, the angle between these two is called Vs. Cos Vs is called sending in power factor. This is the vector diagram of short transmission line. Vector diagram of short transmission line. Okay, I am stopping. We will discuss remaining topics in the next